let's focus more on that ratio of products to reactants that we can use to define and communicate what dynamic equilibrium is for each reaction. And so we're going to do that with what we call equilibrium expressions. We can also call them the law of mass action, which I will always forget to call it that. So, but the law of mass action is just the relationship between the chemical equation and the concentrations of the reactants and the products. And so it's really showing that relationship between the concentration of reactants and the concentration of products in that relationship for any chemical system. And so we can call this the mass action expression. This is also the same thing as our equilibrium expression. Which is, depending on which textbook you're looking at or who you're talking to, and just kind of like what they're the same thing. So what this is doing, again, we've got our forward reaction and our reverse reaction right here. And that creates our kind of two reactions happening at the same time idea of a reversible reaction. So if we just take this super simple version of it, where we have reactant A and reactant B in equilibrium with one another, our mass action expression or our equilibrium expression will be the ratio of the product over the ratio of the reactant. And we're looking at concentrations here in this case, or we could be using partial pressures. And so this ratio right here is going to characterize our what equilibrium is for the expression. And so we're always going to make sure that we remember to put the products on the top and the reactants on the bottom of this fraction. And this fraction is going to be the ratio that you'll use to say, oh, well, the equilibrium for this is blah, 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 and allow you to be able to talk about it and talk about changes to it. So let's take a look at something slightly more complicated, but still using variables than A and B. So for a general chemical equation, and this is the version that we like to use for variables for chemical equations, that you have A plus B goes to C plus D, and it's in equilibrium. Now, the lowercase a, b, c, d are the coefficients. And so that way we can kind of show how the coefficients will work, kind of a format that we can apply to any chemical reaction is the idea here. So if we have this chemical reaction, our law of mass action or our mass action expression or our equilibrium expression is going to be equal to we multiply the concentration of the products to one another, and we have that on the top of our fraction and our reactants concentrations multiplied amongst each other in the denominator. And then we're going to take into account those coefficients and how much the reaction is going to rely on that reactant or product by taking the coefficients and making them the exponent on our concentration. And so for anything, we'll have, so for like C, what this is saying, if C was equal to, let's say, CO2 and little c was equal to 4. So we had something where that had 4 CO2 is one of our products. Then we would write our concentration of CO2 to the power of 4. And so if our concentration was 1 molar, then we would say that this would be 1.0 molar to the 4th power. Great time to grab your calculator and make sure you know how to use it to put in a value and then raise it to any exponent that you want to define what that exponent is. It's a little different on everyone. Let me know if you want some help figuring that out. And so this ratio, this law of mass action, we're going to characterize it with an uppercase K, and that's going to be our equilibrium constant. Remember our rate constant? It was also a K. It was a lowercase k. And now we're going to use an uppercase K because chemistry loves to have similar things that are only different because something is uppercase or lowercase. And here's just another one. We've had a lot of M's this way. Now we get to have a lot of K's this way. So our equilibrium constant, uppercase K, meaning we've got something reversible, is going to be that ratio of products over reactants. So let's look at just some examples of this. So here are the two reactions we've already looked at, and we'll keep looking at through examples. So first I have N2O4 in equilibrium with 2NO2. And so in this one, I'm always going to take, remember, my products over my reactants. Oh, I've got that right here. I don't have to rewrite it. Sorry. So I've got my products over my reactants. And so in this reaction, my reactant is the N2O4, so it's going to go in the bottom. And my NO2 is my product, so it goes on the top. And I have a coefficient of 2. And so I'm going to take that concentration of NO2 that I have and square it. Now, my my coefficient for N2O4 there's nothing. And so that means it's 1. Oops. And so when I put in the concentration to my N2O4, it's really to the power of 1, which is just the same thing that it is. I don't have to actually plug that into my calculator because 1 to the 1 power is 1, or 2 to the 1 power is 2. Like, it is just itself. And so we can calculate what K is based on what these concentrations are at equilibrium if we know them. Now, we already know that reactants are favored in this reaction. And so we know that that concentration of N2O4 is going to be larger than our NO2. And so that means that we're going to have a large number on the bottom of our fraction and a small number on the top, even though that small number, even though it's squared. And so because of that, we end up every time with a K value, equilibrium constant value that is less than 1. So if reactants are favored, then our equilibrium constant will be less than 1. All right. So let's look at our product, or at our other one now. So in this case, we have hydrogen and iodine gas forming 2HI. And so I'm going to make sure that my products go on the top and my reactants go on the bottom. And then I'm going to use those coefficients as the exponents. So I have a coefficient of 2 in front of my HI, so I square the concentration of hydroiodic acid. And both my hydrogen and my iodine have coefficients of 1. So that means I have no exponent on my denominator concentrations. So now we know from what we looked at before that we will have products favored, that our concentration of HI, our hydroiodic acid, will be larger than the hydrogen or the iodine. And so when I set up this expression, I'm going to have a larger number on the top divided by a small number. And that's always going to produce an equilibrium constant that's larger than 1. And so we can see that anytime we have products favoring a reaction, we're going to have an equilibrium constant bigger than 1. Now, if we had the exact same concentrations of each of these, right, then we would have a K equal to 1. So when K is equal to 1, we know that the concentration of our products and our reactants, after we incorporate the coefficients, are the same, or about the same. Let's look at an example, and then you can try one, and I'll show you the solutions. So here is some equilibrium information about hydroiodic acid. So we're forming hydroiodic acid. If you remember, we're combining hydrogen and iodine, and we're forming 2HI. And so our K expression is equal to that HI squared divided by H2 times I2. And so I'm going to put some of this data in and see what I actually get. And I have 2 experiments at different concentrations. So let's see what they produce here. So my first one would have my 0.156 molar squared divided by 0.0222 molar for my hydrogen. And it's the same concentration for my iodine. All right, plugging that just into my calculator, I get equilibrium constant of 49.4. Great. All right, note that that is larger than 1. Therefore, products are favored, which matches what we were doing. Let's do the second trial and see if we get something similar. So I've got a concentration of 0.280 squared divided by 0.035 times 0.045. This is good to point out that you won't always have the exact same concentration of both of your reactants. It really depends on how you start this reaction and their initial amounts and where they're going to end up at equilibrium. And we'll talk about that a little bit later in this lecture series and talk about how do we predict what these equilibrium concentrations are when we only know what we start with. So in this experiment, we are assuming that we are actually measuring these concentrations after the system reaches dynamic equilibrium. And this is actually data that was pulled from an experiment that was able to do that. So these are real values. So calculating this in my calculator, I get a value that is 49.7. These are super similar. They're similar enough with this being real data that we're going to call these basically the same. And that's the idea, that the equilibrium constant isn't going to change just because you start with different amounts of your reactants and products. It's always going to reach the same point of equilibrium, no matter what your starting point is. We'll see some changes in this if we change temperature, but if we keep everything else the same, like temperature, then we should see the same equilibrium constant.